Good morning, everyone, and welcome to this Esri UK webinar in partnership with Scottish and Southern Electricity Networks on the electricity system of the future, how geospatial thinking is driving digital transformation. To start, I will briefly cover off some housekeeping. The webinar is being recorded today, so feel free to revisit this at a later date and recommend it to colleagues who may not be able to make today's call. There won't be a question and answer session. However, we will provide contact details should you have any queries or thoughts to discuss. And finally, we'll be sending out a brief survey after the webinar today. Your time in returning this is very much appreciated, please. My name is Jonathan Swaddle, and I work in Esri UK's Critical National Infrastructure team with my colleagues Craig Bloomfield and Dan Thorburn, who are also on the webinar today. I'm very pleased to announce that we're also joined by Ben Brint from one of Esri UK's key customers in the electricity sector, SSEN. Ben will be sharing details on some of the innovative ways SSEN are looking to transition to the utility of the future. So to start, I have a few quick fire quiz questions. Any thoughts on what 1 million kilometres represents? Well, this is a screenshot from the Energy Networks Association's website, where they note the length of electricity wires in the UK and Ireland, which works out enough to wrap around the Earth 2.5 times. The next one is around what 317 terawatt hours of electricity represents. So admittedly, this is a little tricky, but I'm sure many of you have seen the analysis for future energy scenarios, and this represents our electricity usage in 2022. And what's interesting is if we keep this figure of 317 terawatt hours in mind and move to one of the forecasts for 2050, we can see an increase in over 150% to 801 terawatt hours, which is a staggering increase in electricity usage, requiring significant transition over the years ahead. Final one to finish, and it's $4 trillion. Now, this is the estimated global investment in clean energy by 2030 to meet our 2050 net zero targets. This is a great example of how the challenging transition actually provides opportunity as well, noting the expected job creation here. Further information can be found on the International Energy Agency's website. So why have I selected these figures today as part of this webinar? Well, they go some way to explain the challenges and opportunities that the electricity sector is facing. Esri UK have developed the 7 C's to help summarise some of the challenges, and I'm glad to say it's nothing to do with cod liver oil. We've already touched on the huge uplift in capacity required by 2050 to support the current expected change in demand, with nearly 170% increase. With two-way distribution from distributed energy resources and a whole system approach, further complexity will evolve where spatial thinking can help manage this effectively and safely. With a transition to electricity, its criticality will increase significantly in heating our homes and our transport systems, for example. Furthermore, intricate condition-based risk assessment will be required to proactively maintain assets and ensure return on investment and optimum usage. While demand will rise, we'll also need to see constraints in place to ensure efficient usage, reduce wastage, and influence consumer and prosumer behaviours, driving a flexible system. Cost is key, an issue we've all felt with the recent political turmoil. And finally, cybersecurity is vital. Digitalisation and connected systems will underpin the energy systems of the future, so its security will be paramount. So what we can see is electricity becoming the backbone of our world, requiring an innovative approach in development and significant evolution of today's networks. So what could our networks look like in the future? Clearly, we can't start from scratch, so the transition will build on our current grid and evolve this over time. This will see a huge increase in green energies connecting to the grid. Estimates suggest 500% increase in solar, 200% increase in onshore wind, and 700% increase in offshore wind by 2050. As part of this, we'll see further localized generation through distributed energy resources, which will improve resilience. In addition, new sources such as biomethane will be introduced, along with battery storage, helping balance demand. Furthermore, a flexible market will be introduced to incentivize customers' access and potentially provide energy to the grid as prosumers. We'll see a ramp up in IoT devices, helping consumers and system managers control usage effectively from a house level through to a national level. And to make all this happen effectively, efficiently, and safely, an innovative approach is required, along with central control through a whole system approach. And this is where geospatial thinking can help shape a new approach, drive change, and help recognise efficiencies. So how have Esri UK shaped a strategy to help the sector tackle these opportunities and challenges? Well, in working with key contacts in the sector and with our customers, we have evolved this strategy wheel. The template has evolved through review of GIS and digitalisation strategies, and also brings in ideas and best practice from around the world. Cross-cutting themes, net zero, health and safety, innovation sit at its heart and apply to all sectors as we evolve out the next layer of segments. These 5 segments act as umbrella terms to focus on key areas of importance, which we can then break down around the wheel. A geographic approach can help all these elements, and it's some of these that our demonstrations are going to explore today. I'll now pass over to Craig, Customer Success Manager at Esri UK, to introduce the first of our 5 demonstrations. Craig, over to you.
Thanks, Jonathan. So as Jonathan mentioned, we need to evolve our current energy network to support renewable energies moving towards the 2050 goal of achieving net zero carbon. The first of these topics we're going to look at today is digital twins. How can a digital twin support a whole system approach? How can we start to look at our network and join the dots? Join the connections between generation, transmission, distribution, and consumption. And on this note, I'm going to hand over to Dan, who's going to explore a little bit further as to what a digital twin is and how it can help in this scenario. Over to you, Dan.
Thanks, Craig. Well, a digital twin is a concept that involves creating a virtual representation or model of a physical object, a system, or environment. It allows for the integration of data, simulation, and analytics to understand and interact with a real-world counterpart. Now, while the term digital twin may be relatively new, the idea behind it is not. So in fact, GIS, or Geographic Information Systems, has always functioned as a form of digital twin. Now, GIS at its core is a technology that captures, analyzes, and visualizes spatial data, providing a digital representation of the real world. It serves as a bridge between various systems and data sources by using location as a powerful key or reference. GIS enables us to understand how information from one system relates to another by leveraging the spatial context. When we consider the stages of digital twins, we can see how GIS aligns with them. The first stage is capture, which involves collecting and gathering relevant data. GIS excels in this aspect as it enables the collection of geospatial data from diverse sources such as satellite imagery, surveys, sensors, and more. The next stage is visualization, where the collected data is organized and presented in a meaningful way. Now, GIS allows us to create maps and charts and visual representations that provide context and help us understand the relationships between different elements of the real world. So the analytical stage comes next, where spatial analysis techniques are applied to the data. GIS enables us to perform various analyses such as proximity analysis, network analysis, spatial clustering, and much more. And these analyses help us gain insights and discover patterns and make informed decisions based on the spatial relationships within the data. Moving forward, the real-time stage involves integrating real-time data feeds into the digital twin model. Now, GIS platforms can incorporate live data streams such as weather information or traffic data or sensor data to provide an up-to-date and dynamic representation of the real world. As we progress, the semi-autonomous stage emerges where artificial intelligence algorithms and machine learning techniques are applied to the digital twin. AI algorithms can analyze the real-time data, spot patterns and trends, make predictions, and even take actions to optimize or resolve situations. And this level of maturity empowers decision makers with intelligent insights and recommendations. And lastly, the fully autonomous stage represents the pinnacle of digital twin maturity. At this stage, the digital twin becomes a comprehensive and evolving model of the natural and built environment. It incorporates data from multiple sources, from agencies and systems, representing the complex interactions and relationships between different elements. The fully autonomous digital twin learns, it optimizes itself, and can make decisions independently, functioning as a living, breathing representation of our world. Now, it's worth noting that the concept of digital twin can vary in meaning and scope across different sectors and industries. However, by understanding the stages of digital twins, we can appreciate how GIS has always been a form of digital twin in capturing and visualizing and analyzing and integrating geospatial data to create a comprehensive understanding of our environment. As a business and society, we aren't quite at the autonomous maturity level yet. But using location, our aspiration is to get to the stage where we can develop a picture report of the city, an interconnecting view of multiple digital twins, road networks, buildings, green spaces, something tangible that customers, stakeholders, and non-technical audiences can click on to see the current status of a project or a substation or planned works. The opportunities here are endless. Craig, back to you.
Brilliant, thank you, Dan. So as Dan's shown there briefly, the digital twin is going to become a critical part of evolving our network over the coming years. And as you saw, 3D and BIM, building information modelling, is going to be a critical part of that infrastructure planning and design to support the aspirations of the energy industry. This next section, Dan's going to go into a little bit more detail about how 3D and BIM can support the planning process and help him make informed decisions going forward. Back to you, Dan.
Thanks, Craig. So let's have a look at what is BIM and where does GIS fit in. So BIM, as Craig's mentioned, is short for Building Information Modeling, and this really focuses on capturing detailed information about built assets. It provides a digital representation of physical structures, capturing attributes such as geometry, materials, and performance data. BIM models contain rich and accurate information about individual building components, including the walls, the floors, HVAC systems, electrical networks, and much more. And this level of detail facilitates design, construction, and maintenance processes by enabling precise coordination, clash detection, and asset management throughout the building lifecycle. On the other hand, GIS provides information about assets in a broader context of the built and natural environment. GIS integrates spatial data with attribute information, allowing users to visualize, analyze, and interpret data in a geographic context. It encompasses not only the built structures, but also the surrounding terrain, the land use, transportation networks, natural resources, and environmental features. And GIS enables users to understand how assets are interconnected with the surrounding environment, facilitating spatial analysis, decision-making, and planning. When BIM and GIS are integrated, they create a really powerful synergy. By combining detailed building information from BIM with the spatial context provided by GIS, stakeholders can make more informed decisions and gain a deeper understanding of the built environment. This integration enables stakeholders to analyze the impact of building assets on the surrounding area, assess potential risks, and optimize resource allocation. For instance, by overlaying BIM data onto a GIS platform, facility managers can visualize the location of specific building components within their broader geographic context. This integration allows them to analyze the impact of facility maintenance or renovations on surrounding infrastructure, utilities, and natural resources. To demonstrate the power of bringing GIS and BIM together, I'm going to show you a couple of web scenes. Now, web scenes are a type of viewer that can be created in ArcGIS Online or Enterprise. What we can see in this scene is some base mapping and imagery, as well as 3D features like buildings and trees. The key thing about a web scene is that it's in the web, so it's accessed through a browser and therefore doesn't need any specialized software to be installed. As with any other application, you can restrict who has access to it, be that just a couple of colleagues, the wider group, or your stakeholders, or even the general public. Now, in this example on the screen, when I click on one of these bookmarks, I'm zoomed out of the city into another area of the map. And when this loads, what we'll be looking at is a BIM model. So I can click on the model to see more information about it. We'll see that pop up on the right-hand side. And likewise, I can go ahead and click on a cable here and see more information about that too. And I can do this because I can publish BIM files out of ArcGIS Pro, our desktop software, into ArcGIS Online or Enterprise, and it will pick up all of this information within that model. So what I want to do is go and have a look at a distribution example. So we'll be zooming out and moving to another part of the city in this web scene. And again, we can see the same thing happening. So I can see the models in the context of the surrounding area, and I can access the information about them. And another data set that really is just for interest, but something I think is worth showing that we can publish is LiDAR, be that flown by yourselves or obtained from a third party. And what you can see is this data set really starts to give detail to the web scene and allows comparison of heights, for example, on buildings or trees. Now, I've got one more web scene to show you, and in this one, I want to highlight a couple of other features of a web scene. So you can see this one's really similar to the last one. We've got buildings, trees, and base mapping. And again, we can choose some of these bookmarks to take us to a model. And what we'll see is a really detailed model sat here with its contextual base mapping and surrounding buildings. And from within the web scene, we can start to explore the building level by level, again, clicking on assets for more information. The next example I'm going to show you is, again, a BIM model, but with a bit more detail, which we can, again, explore using the Building Explorer. And this time we've got all of the mechanical assets here as well, which we can toggle on and off, for example. And we can see things like pipework in this example, but this could equally be cables or any other elements of a BIM model. And finally, so one last example in the web scene, and this one is an underground development. So again, rather complex, but what we're using the Building Explorer for this time is to allow us to cycle through different construction phases. Okay, that's all from me on BIM, so back to you, Craig.
Brilliant, thank you for that, Dan. So we've started to look at how to visualize your data, how to start building your digital twin. Now, next we're going to look at field mobility and how GIS information and your data can be disseminated across your user base, whether out in the field, in an offline or offline capability, and how they can use this in certain scenarios, how they can bring in data and have access to things like weather data in the field, how they can use your data for things like site inspections, asset updates, looking at instances of damage, repair, and Dan's going to show an example or a couple of examples here of how this can be undertaken. Back to you, Dan.
Thanks, Craig. So we've got a really wide range of mobile applications to cover really the whole life cycle of works. And this could be from planning work all the way through to capturing simple or complex data, and then even potentially tracking and monitoring data collected or users in the field. So you can see on the screen now a range of products which all answer a specific problem. And the one you're going to see most often is ArcGIS field maps. And that's what we'll focus on in this use case today. So what is ArcGIS field maps? Well, it's designed to replace the paper processes with an all-in-one solution for collecting data in the field. Maps are created for the app in a web browser and shared either to groups or the organization, which field operatives can then access. And there's the ability to download an area of map and data to ensure that the operative still has access while working offline. Now, the map could include both network and non-network data, or pretty much any data that you've got in your ArcGIS Online or enterprise environment. And this can be pushed out to field maps, and it can be set to read-only or editable. Some other features are the ability to track your location, so you could walk a route and it will capture that as data. We'll see that in a moment. And you can increase the accuracy with high accuracy GNSS devices, as well as capturing data. You can capture something called markups, which could just be notes to self sort of thing, but are shareable with your organization. So on the screen now, you can see a basic management dashboard on the left, which could be monitored back in the office, and the field maps interface for mobile on the right, which I use in this instance as an engineer on site. So what I'll do is take you through a quick demonstration of this, and I'm going to undertake a few tasks in field maps, which will be reflected in the dashboard. So firstly, managers can see more information about me by clicking on my location. And equally, I can see that I need to review a fault report at this location. So again, I can click on it to see more information. But while I'm here, I also need to report any other issues that I see with the site. So we can see in the app that I have a map with layers from the ArcGIS system within it, and I'm connected right now. So any changes I make will be reflected in the rest of the system right away. But I could equally download an offline copy of the map and layers and sync them back when I get connectivity. So I've turned on location sharing, which means that my location is being recorded. So we'll see as I move around the site, we can see the blue line start to generate. Now this is great as a reference for me, but we could also convert this to a data layer if needed. This also means that the manager back in the office can track my location, as we can see in the dashboard. Now before we go too far, I've just used the markup function to drop a note as to where I've parked. And throughout the demo, we'll just speed up a little bit and move further north up the road. And we'll see that as I get closer to the site, I'll get a warning pop up advising me that I'm about 200 meters away. Now this is enabled through a feature called geofencing. And geofencing is set up in the web builder for field maps, so in advance of deploying to a site. And this allows us to generate warnings when entering or exiting defined zones. Now, as I head towards my job, I notice another one of our assets has been vandalized, and I need to record this. So I can choose the observations layer to digitize a point into, and I can adjust the position and use snapping to get it onto the asset. Now we can go ahead and choose other in the drop-down, which you can see opened up some fields, and I can put free text into this. In this case, we're choosing vandalism. Equally, I can attach photos either directly from taking a picture on the camera or from my photo reel on my device. So as we continue moving north up the road, we'll see that I get another warning from a geofence advising that I'm now at the site and must ensure that I'm wearing the appropriate PPE. If I had wearable tech on, such as an Apple Watch that's connected to my device, it would also push a notification through that to let me know as well. So once we reach the site, I can open up the information about the site from the data that's loaded into my application. I can go ahead and start to review it and maybe take a look at any attachments that it might have, and really just make any changes as needed. So for now, for this job, what we'll do is we'll mark it as check complete. And once this is submitted on my end with connectivity, we'll see that the manager can pick this up in the dashboard instantaneously. If this was offline, we would have to wait to get connectivity before we can sync back up and send the report back in. Craig, back to you for biodiversity.
Brilliant. Thanks very much, Dan. So the next stage in the demo today is going to be looking at a couple of topics called natural capital and biodiversity net gain. And Dan shortly is going to explain what this means. As an energy industry, to achieve our goals and to increase the performance and energy which is going to be consumed over the next 20 to 30 years, obviously a great deal of infrastructure is going to have to be created. Now, as an industry, we have a duty of care to maintain our environment as we move towards that net zero carbon placeholder. So Dan's going to go into a little bit more detail about how this is going to be achieved through the biodiversity and natural capital projects. Over to you, Dan.
Thanks, Craig. Well, firstly, let's have a look at what do I mean by, or what do we mean by natural capital and biodiversity net gain. Natural capital is the Earth's stock of natural resources and ecosystems, so recognizing them is essential for human well-being and economic prosperity. Preserving natural capital is crucial for maintaining our quality of life and the planet's future, and its value can now be compared to economic assets. This prompts many organizations to take action and assess their impact on or the protection of and really better utilization of natural capital, aligning with the United Nations Sustainable Development Goals. Knowing where natural capital assets are in relation to other global features is vital. For instance, a woodland's value could vary significantly depending on its location, such as being near a city with higher social and recreational value, or in the north of Scotland near a moorland with potential for habitat conservation, carbon storage, or timber resources. And knowing the location of natural capital is crucial for making well-informed decisions. Starting in November 2023, England's planning developments will be required to adopt biodiversity net gain, which means developers must restore and enhance 10% more habitat than they remove. This approach highlights the significance of considering the area's existing natural capital and assessing its impact to plan appropriate measures for conservation and compensation. And electrical companies are impacted by this and so are committed to achieving that 10% net gain for new major projects. Now, to demonstrate where GIS can start to address the elements of biodiversity net gain or B&G submissions, I'm going to show how an ecologist in the field can use field maps to collect a habitat baseline, how a designer in the office can use Suite for ArcGIS to start to plan out scenarios for a site, and how a biodiversity manager might use Experience Builder to share that information with stakeholders. So first, as an ecologist, I need to capture the habitat on site. And I could be doing this to assess a site for a new asset, or I could be doing it as part of an ongoing monitoring project. And I'm going to do this in ArcGIS field maps in this case. So the first thing I can do is have a look at the different layers in my map and just turn them on and off as required. Now, to capture the boundary of a field, I'll use the new feature tool and add vertices of my field. And once I've done that, we can start to fill in some attribute information such as grassland, the type of grassland, its condition and its strategic significance. This will calculate the total habitat units for me, and in here I could also change the attribute information to woodland, and we'll see that this updates the habitat units automatically. So now I'm going to use something called Suite for ArcGIS to help with planning out improvements to the site, perhaps a new substation, or to make sure I'm meeting biodiversity net gain targets. So you can see here we have the now fully completed habitat baseline. The first thing I'm going to do is plan out some additional woodland because I know that that's a good quality habitat. And I can see that Suite is giving me a warning that there's a breeding bird area here. And it's doing that by picking up on an underlying layer to provide me with the responsive map feedback. When I complete this area of woodland, you'll see that it's reshaped as I have a rule here saying I can't plan outside of my study area. And in the custom panel, we get a responsive feedback on the biodiversity score. And we want to improve that, which we can do so utilizing certain attribute rules. So at the moment, we can see the total baseline units, much like in field maps, we can go ahead and change the habitat or the condition, and those units will be updated automatically. Another thing I can do to improve the score is I can reshape the habitat. And you can see that the field next to its boundaries will change and update as well, and that's because they're topologically connected. And lastly, I'm going to create a pond using something called a smart template. And we'll draw that using a freehand tool to give it a more natural shape. You'll see that if I try and put it next to the public right of way, I get some more map feedback telling me that I can't design here. So instead, we're going to draw the pond just to the south. And we'll see that the smart template has drawn not only a pond, but the reed bed, a life ring, and all at the same time, which has bumped our biodiversity score up into the 90s. Now, as I'm happy with my proposed changes, I can now look to share that with my stakeholders, and I can do that using a web application built in Experience Builder. In here, I can search for the relevant site, and you'll see that we have the habitat baseline here, which can be filtered using a pie chart. In the app, I might also be interested in the loss. So this is our proposed new substation, and we can see the habitat lost in the area as well. In the mitigation tab, we have a design. So this is where we could draw it in suite. And again, I can filter the habitat just to see the relevant types. And finally, we have a summary page where we can see each one side by side with their biodiversity units. And if we wanted to, we could also view this in 3D as well. So we can get a much more immersive experience, really bringing to life the proposals. Craig, back to you.
Brilliant, thanks for that, Dan. So the next section, I'm going to hand over to a colleague, Ben Brint from SSE Networks. I've worked with SSE for a number of years now, and it's impressed me in the innovation that they've been working on within their business to look at how they manage their network, how they're creating innovative ways to understand and respond to the challenges that a growing network introduces. So on that note, Ben, I'll hand over to you and let you explain what you've been doing.
Good morning. Thanks for the introduction, Craig. I'll be talking about a project which has used GIS to analyze and combine multiple data sources to solve a very specific problem. SSEN has been investigating the feasibility of dynamic line rating on long circuits, and I appreciate that might not mean much to a lot of people. I'll firstly describe what dynamic line rating is, otherwise known as DLR, and then I'll go on to discuss what's led us to develop a solution centered around geospatial data. SSEN Transmission owns and operates the transmission network in the north of Scotland. The area is seeing unprecedented growth in capacity requirements, mainly due to geographically dispersed variable generation sources such as wind farms. These connections need to be made to meet our license obligations, but also to facilitate the government's net zero targets. The speed at which we must develop and grow our network is a challenge, with typical large infrastructure projects taking years to develop, design, and build. This has resulted in us coupling our traditional operating techniques, such as building new lines, with innovative methods such as DLR to operate our current infrastructure. In order to do this, we need to develop our current techniques to allow us to estimate potential uplift that could be provided by a DLR-enabled circuit. Our project's overall objective is to estimate the reduction in constraint experienced by a 150-kilometer 275 kV circuit between Beaulieu and Duray, highlighted by the red line on the photo in the top right. But firstly, some basic overhead line terminology. The top left shows a photo that most people are familiar with. Overhead lines are consistent of multiple components. The two most recognizable are the tower or pylon and the conductor, which is the cable strung between the towers and is what transports the electricity. All conductors have a maximum operating temperature. The maximum operating temperature is in place to protect the asset's integrity, expand its lifespan, and to ensure the conductor does not sag too low. This is because as the conductor gets hotter, it expands due to its metallic nature, and therefore becomes longer and closer to the ground. The temperature of the conductor can be determined by a relatively simple heat balance equation. The heat into the conductor will become equal to the heat out over a period of time. The heat in the conductor is caused by the current or the electricity flowing through the conductor, which causes heat due to the resistance of the metallic material. Weather can also cause heating to the conductor through solar radiation and ambient temperature, if it's warm, of course. Conductor cooling is typically from wind flow, radiative cooling, and ambient temperature if it's cool. Currently within the UK, we rate our conductors statically on a seasonal basis, meaning they only change 4 times a year. This means we utilise very conservative weather data to ensure we do not exceed the conductor's maximum temperature. This is particularly evident in the wind speed. As you can see in the table, we use a wind speed of 0.5 meters per second. 0.5 meters per second is a low wind speed, particularly in the north of Scotland and areas where wind farms are due to be or are currently operating. As the problem definition has set out, the UK grid is undergoing a period of rapid change in which we need to provide more capacity as quickly as possible. If we would change to a dynamic rating methodology where we input real-time weather data at hourly intervals, massively reducing the factors of safety that we need to be applied to our static ratings, we may be able to very quickly reduce the constraint on some of our circuits. When we first looked at the objective, we were met with a large geographic area and very limited data processing resource. In order to reach an initial conclusion, in a suitable amount of time, a high-level approach was taken. Firstly, the circuit was segmented in order to differentiate its varying orientations, and more importantly, the angle of wind flow across the conductor. This was done by creating a new segment every time the orientation of the circuit changed more than 10 degrees. The focus then shifted to identifying and allocating sparsely located synoptic weather stations and calculating the line rating for each one of the segments identified using the closest geographic weather station and industry standard line rating equations. Further to this, the estimated generation in the area was also counted using the same weather data and a generic wind turbine power curve, coupled with the geographic location of the wind farms that are currently and planned to be connected to the grid. The result of this high-level evaluation is shown in the graph on the slide. The dark blue line showing the predicted generation, the light blue line showing the estimated dynamic line rating, the red line shows the static rating, which is currently imposed upon that circuit. The graph shows from this high-level evaluation that DLR is feasible. The light blue line is higher than the dark blue line, and is worthwhile exploring further. It highlights correlation between the wind generation and dynamic line rating. It was felt that although the high-level evaluation provided reasonable evidence to commit resource, it did not provide estimated values that could be fully relied upon, mainly due to a lack of accurate weather data. Furthermore, the method did not allow for identification of pinch points. Pinch points are areas of the circuit which experience the least favorable rating conditions, i.e. low wind speeds and high solar radiation. Without identifying these areas, it's impossible to target asset monitoring without blanketing the whole circuit. This resulted in the development of a methodology with greater granularity to fill the gaps identified. Whilst developing the methodology of the desired granularity, a change of tact was taken. We'd been focused on using weather data in our analysis, something which is extremely variable across terrain and very changeable year on year. This, coupled with the sparse nature of synoptic weather stations in the north of Scotland, led us to focus on a terrain-based approach. The abundance of high-quality static topological data meant that highly granular analysis could be produced. In conjunction with the Met Office, the topological factors which affect the key weather parameters of dynamic line rating the most were identified. These topological factors were finalised as land dissection, which identifies areas prone to shelter, slope, which identifies exposed hilltops and deep valleys, altitude, which identifies areas of high daytime temperature, and heat load index, able to identify areas of high solar radiation, were assessed using GIS to record the data geospatially. An idea for the output can be seen on the screen now. The combination of all the data identified on the previous slide would have been a challenge without the use of GIS. The formula and weightings in the bottom left of the screen show how the data has been combined. The resultant output being the map shown on the screen. This map highlights areas at risk of being exposed to unfavourable rating conditions, allowing us to strategically mount conductor-mounted equipment to measure in real time the conductor's temperature. Further to this, as the pinch point locations are ranked due to risk, a decision can be made as to how many sensors are required for safe operation of dynamic line rating. Now that we've accurately identified the pinch points, we're able to reintroduce weather parameters. The Met Office provided wind speed and direction using the virtual Met mass methodology, and ambient temperature and solar radiation, producing a similar looking graph to the previous analysis, again comparing estimated generation and dynamic line rating. The key differences between the two approaches are the ability to identify pinch points, and this is down to the line-specific data that can be produced. Interestingly, we can see greater disparity between dynamic line rating and the estimated generation in this approach. However, given the circuit is approximately 150 kilometers long, this is not unexpected and highlights the more granular weather data is providing greater geographic separation. This methodology allowed us to produce accurate estimated uplift figures to provide to our system planning teams to determine dynamic line ratings value to our network. Further studies have been identified to progress this methodology. Firstly, further research and development into the weighting of topological factors, and secondly, to enable the Bewley-to-Dunray circuit, the one that was previously assessed, with DLR sensors in order to verify the estimation methodology. In summary, looking at the initial problem statement, this study has demonstrated that DLR can provide an increased capacity or decreasing constraint and allow us to provide system planning teams with accurate estimates, allowing them to correctly focus projects on strengthening and growing the network. DLR has a quick install time, and now a detailed but quick methodology has been developed, so the design process also allows for rapid rollout where required, helping to enable the net zero transition. Finally, we have advanced our current techniques by developing this novel approach of utilizing topological factors to make an assessment of a weather-based problem, allowing us to inform our regulator and business and allowing them to make a decision centered around a realistic cost-benefit analysis. Thank you.
Thank you, Ben. It's been great to see how SSEN are making the most of a geographic approach in evolving the business. So thank you for your time and sharing that on the call today. To briefly recap on what we've seen today, we began by looking at how a digital twin will underpin the utility of the future and a whole system approach. One of the key values of this asset is its ability to drive engagement and collaboration with a utopian vision of a common digital twin across industries, not just focused on electricity. Next, we looked at how design and planning functions can be enhanced through connecting data from CAD environments and visualizing this in the most appropriate way for end users to work with. 3D facilities are already accelerating in their usage, and the utility of the future will help inform stakeholders through this more representative data capability. We saw how critical informing and enabling field workers is next. Having timely information in the field is vital for health and safety, inspections, maintenance tasks, and emergency response. ArcGIS provides online and offline working, supporting our customers' mobile requirements 24/7. Natural capital and biodiversity net gain are now key to working procedures, so using a spatial approach to understanding the baseline and reduce impact in the future is crucial. From new electric vehicle charging points to transmission lines to further wind turbine generation sites, We know large-scale development is required to meet demand, so minimising impacts proactively is key. Then finally, we heard from Ben around how SSEN is using innovation to fine-tune how they maximise the use of assets that they currently have in place. Innovation like this will prove vital for the utility of the future in helping run the whole system as efficiently as possible and maximising the use of assets accordingly. So we have covered quite a few topics today on the webinar. I hope you found them of interest and thought-provoking. We intend to run a further webinar to explore more elements of the strategic template wheel. So if there are any of particular interest, then please let me know. In addition, if you have any thoughts or questions, contact me at jswaddle@esriuk.com and I'll work with the Esri UK colleagues and Ben to respond. The survey is available on screen now, but we will send this out round via email as well and really appreciate your feedback. So thank you for your time today, and I hope to catch up soon as we collaborate further with the electricity sector in the future. Thank you.